Okay, thank you for everyone to joining. So today just want to give a presentation for this 100 story super high rise. See how we are building it and what kind of challenge that we are facing. So this particular project is located in Kuala Lumpur, Malaysia. The initial name was Signature Tower, and later it changed to Exchange 106. This particular tower is already topped off. You can see the construction on this particular photo is almost done. The client is a developer named Molia Development. They also are the architect and contractor as well. The construction cost for this particular tower is around 700 million. The scale of the tower is 106 as the name, 106 level, which have like 92 floors office, and then there's some like 6-story basement, and there's a crown on top of it. So you can see this is the elevation view and section view of the tower. It's really tall, and then there's three portions of it. One is the basement, which is connected to the metro system. And then there's a main tower, and then on top of it is the crown. This particular tower, it will be the 15th tallest building in the world, which might be one of the lifetime project, in our lifetime. There's more than like 2,000 workers was working on it. And make it, this particular one is really sufficient and efficient, which top off, in 17 months. Thank you for the construction team. And this is also a true Class A building, which means the design, all this architectural features is meeting the true Class A. There's not that many true Class A building in the world. So I'm gonna give you a little video, which is a time lap, during the construction. You can see how it builds. There's 2 core, and then there's sloping column at the exterior. There are many cranes to help the construction. The 3 crane attaching to the core, it's self-climbing crane that it can keep going up by itself. So pretty soon you can see the completion of the tower. This tower is simple in a way, but it's really efficient in another way. Let's talk about the tower foundations. There's one big challenge, for the super high rise. There's going to be a really big challenge on the foundation. This particular foundation is a little bit special than what we normally experience, which is a piled raft system. This is, which means both the soil and the pile act together for the foundations. During the design, we have to do many integration between geotech and us to find out the stiffness between the limestone and the board pile. So we have a range of it, and we do multiple runs and then come up with the worst mat reinforcing conditions. So the mat came up to be like 4.2 meter deep. There's 1.8 meter and 2 meter board pile supporting it. The whole foundation mat takes 2 days continuous pour, which is a second largest, pour at the time, which included a lot of design effort, preparation, and means on the mix. And also there's a lot of rebar detailing and laying out, coordination doing the design. I'm going to show you another video, so which is how they are doing a pour. So, the coordination including, in the plan, the design, the makes. There's a lot of data that's showing up on the video. Doing this big pour, there's a lot of heat generated. So they also use ice to cool down the heat. So this, just keep it in mind, it's a non-stop 2 days continuous pour. So this is between top and bottom mat. There's a lot of workers. 4.2 meter, so you can have your own room there, a big room. Okay, that Chinese wording, it just say successfully. Okay, so the tower is founded with dual core shear wall. This shear wall it's according to the elevator layout as well, the elevator and the stair layout. So it will drop when the floor goes up. There's 2 full floor height outrigger truss to help the drift on the building. One is at 48 and one is at 87. All the column is sloping as all the perimeters column is sloping as I mentioned before. And then we also use a composite floor truss to reduce the steel usage. You know, in Malaysia, the labor is much cheaper than in US. So every little material we can save, that will mean saving money. And then we also, you know, have a lot of simplified detail and pretty consistent detail. So one is to speed up and the other one is to minimize the construction error. So you can see this is the floor plan, one of the floor. And then with the shear wall details. And then there's a lot of boundary elements, steel in the wall. And also there's outrigger and belt truss. So all this detail put together need to be really precise. And we detail almost every conditions. So make sure that the, you know, is constructible. So this is the some construction photos on the wall. So we standardize the shear wall boundary, the casing, which is built in a on-site shop. So they do have a shop on site to build all this casing, and then they live and couple it, you know, on the field, which can speed up the constructions. So we use ETAP 3D analysis to do our design. This in Malaysia, Kuala Lumpur is surprisingly is low seismic, which is only at 0.105 G. And then we do have a wind tunnel study and wind tunnel force that we need to apply to design the tower, which is 35.9 meter per second, equivalent to about 80 mile per hour in our code. And we also use important factor of 1.25 in our design too. So during the design, we have two stages. One is ultimate limit stage for 100 years. So which means when we design all the strain of the elements, so we design for 100-year wind. And then there's a serviceability level. And then we limit it to H over high over 500, which is 500 year for comfort level. During the design, there are big challenge that our engineer find out there's a lot of steel is overstressed. And it doesn't matter how big we increase them, it's still not working well. So we peel down the cost by removing or looking at each individual low case to find out what is causing that problem. So what we find out is there's a differential settlement or shrinkage on the concrete, between the concrete and the perimeter steel column, which creating a displacement between those two elements and have a huge force due to the displacement. We come up with a solutions doing a step construction sequencing, which is another challenge, for the modeling too. So we put down the step in each conditions and each loading, it all different, and then the connection will be quite special. So we generated a construction sequence which match our analysis to reduce the this displacement kind of effect to the elements, which works out pretty well. There's another big challenge is this 58 meter tall crane, which is equivalent to about 15 floors. This crane, it's a separate element, so it's not part of the tower. We designed it in a we analyzed it in a SAP model, and then we put in the reactions to the tower to understand the effect of this crane. The wind tunnel also have this crane built in. We feel this crane is pretty important element. So we bump up the wind force to 58 meter per second, 50 mile, which equivalent to 130 mile per hour. Which is going to be pretty safe in our opinion. And then this particular crane have more than 1,000 kind of 3D welded joint, connect them together. Also, you can see there's kind of a net shape system. We find is really good working system for the high wind. Interconnected elements together. And then we also have helped the construction team, with a 3D model and doing the constructions. So every sequence, is precisely detailed, and the join, some of the join is offset to make the constructability, doable. So that's about the challenge for the structure itself, the tower. So there's quite a lot of architectural challenge in this project too. One of them is a 36-meter, long span, 2-story kind of long cantilever floor that it creating a column-free space at the lobby. Let me show you this plan. You can see there's one big truss, which is a Rivendell truss. So adding like 2 floors, which is a main truss there, and creating a free space below. And also you can see a round staircase. Before we don't have any column that the architect or the owner want us to do. So we utilize this staircase to a structural element and put in a big cantilever and support, from this circular staircase. So just like Danny was saying, be creative. And then there's an other challenge is there's some 5-story high curve fin, along the face of the building. This is they want it to be freestanding, but unfortunately, it's really difficult to do. So we tie them back to the floor, but in certain locations, not all locations. Well, obviously they like the high floor. So there's the main lobby with 21-meter height, with a lot of connecting bridges and escalators. Obviously, at the basement, there's a main traffic going on at the lowest floor. So architect asked us to create a big wide lane for the traffic. So we came up with a sloping column idea. And doing this one, there's a huge kick-out force at the bottom, and at the bottom of the beam. So we have to design for those kick-out forces as well. One more thing is, I had mentioned a little bit before, but I just let you know there's 36 elevators in different zones. So they have low zone, mid zone, high zone, super high zone. So there's many elevators. So I counted, there's 36 of them. So it's pretty interesting. So the dual core shear wall is shrink, to accommodate that as well. So that's about my presentations. No questions? Thank you. Okay, now it's open up for questions. Anybody have questions?
Hey, Charles.
Yes.
What is the floor truss system that you're talking about?
The floor truss?
Yes, for gravity only.
Oh, that's regular, I think it's built by Angles. The floor, the composite truss you was talking about?
Yeah. Instead of a wide flange, it's like a built-up member.
Yeah, we build up with Angles, I believe. Or WT and Angles. And then we analyze it with composite. So there's a special way of do that. I don't believe RAM have any way of doing it.
Hey Charles, this is Pete. How do you decide where the belt trusses go, the outrigger trusses? But two different elevations.
Mm-hmm. During the design, we tested, a couple locations. Normally, we wanted to have one close to the, higher is better. And the highest one we can get is 87. So that's pretty much set. And then the other one will be, at the mid-height between them. So that's how we find out the 47 is in other locations.
Hey, Charles.
Yes.
This is Kevin from San Jose. And how do you get the cranes to continue up the high rise during construction? I know that's kind of like a means and method, but I'm wondering if you knew.
Oh, the crane have, it's, they have some kind of embedment to the wall, and then they jack itself up to a next support. So it just keep climbing it up on the wall. Does that answer your question?
Yeah, that answers it. Thanks.
Yeah. So it jacks itself up and then it attached to the next support.
Hi Charles, this is Yusuf speaking from Istanbul. Can I have a question?
Yes.
First of all, thank you for this nice presentation. My question is related to outrigger trusses. Was it a kind of BRB or conventional member?
No, it's not a BRB member. It's a wide flange member. And some of them is built up too. Because
so I guess most probably because of the location is not high seismic area, right?
Correct.
Okay, thank you.
All right.
Hi, this is Sean from San Francisco.
Hi, Sean.
Hi. I'm at the office, still watching your presentation though, on a different floor. But
Yeah.
So wind acceleration, was there a wind acceleration criteria as well, or was that the drift criteria sort of analogous to a wind acceleration criteria per lateral?
The wind deflection criteria, it's a standard, I believe, in the industrial standard. And then we kind of work with the wind tunnel engineer to come up with that criteria. And the wind tunnel report will provide us the applied force to each level.
As far as the human comfort on the floor, how does the drift relate to the human comfort on the floor? For example, the swaying and the accelerations that we feel.
Yeah, the wind tunnel report adjusted the human comfort, associated with the building property. So there's an acceleration report. It's all come from the wind tunnel study.
Understood.
So we did adjust, some of our stiffness, to accommodate the wind comfort. Yeah. And one thing I just want to mention that if I know that crown is be that big, I will include it, as a lateral system. Before, there's not that big of the crown and totally different shape. But also there's some challenge over there. The crown have, some transfer column that architects don't want us to go down to connected to the perimeter columns. So, any other questions?
Hey, Charles.
Hey, Charles.
Charles, can you hear me?
Yes.
Okay. Charles, can you hear me?
Yes, I can hear you, but I didn't hear the question.
The question is, do you have moment frames around the perimeter of the building, or is it just all concrete core?
No moment frames. There's some moment frame at the lower floor, lower level because the concrete core is not there. So we use moment frames at the lower levels, not at the upper level.
Hey Charles, this is Jonathan. Can you tell us like how you work out the fee for this? Do you give one big huge fee in the beginning, or are you doing some kind of hourly fee later on? And then how about when there's changes? Are you doing change orders for all the architectural different changes? And in the end, were you profitable?
Yeah, the fee is pretty low. The way it's set up, we design up to DD. But our drawing is like 95% of CD, equivalent to, in our standard here. But they only pay us the DD fee. So answer your questions. So we do have the DD fee, and then later on we got this change, and then we get some change orders at fee, later on. And even on the like the wind load study update, we got some additional fee for that too. So you just need to work with the client, I believe, to negotiating the fees.
Hey, Charles, are you there? Can you hear me?
Yes.
This is Bob.
Yes.
Hey, question for you on the sloping columns. I imagine it's much more efficient to do sloping columns at the base than a transfer girder somewhere along the line. Can you talk about that a little bit?
Sloping column.
The two columns that you pushed out to get the
The
pathway
transfer
through.
sloping column.
Yeah, right.
Because that two column is a perimeter column, is supporting the full height shear wall. So transfer will get us a huge shear problem. And then for the sloping column, that minimize that. So that was the reason that we use a sloping column versus a transfer beam. Yeah, in other location we do have some transfer, but not to support like 90 some floor up above.
Yeah,
That's
right.
not a good idea.
Thank you.
Okay, we're all good. Thank you, everybody.